You know that feeling when you just look up at the night sky? It's
Yeah.
beautiful, sure. But if you stare long enough, it starts to feel really heavy.
Heavy, like in an existential way.
Yeah, exactly. I mean, you know the stats. Billions of stars, billions of years. Just
Mm.
basic probability says the sky should be absolutely buzzing with traffic. We should be seeing Dyson spheres or, catching stray radio signals.
Right, the classic Fermi paradox, where is everybody?
Right. And instead, it's just this crushing silence. It's not just a fun dinner party topic anymore. It's becoming this actual weight. We're alone.
It really is the loudest silence in history, and usually when we try to answer it, we look at biology, like maybe life is just super rare, or sociology, maybe civilizations inevitably blow themselves up.
Yeah, the great filter. We just assume they died out.
But what if they didn't? What if they are alive, thriving, incredibly advanced, but they are physically trapped?
Trapped. Like in a prison.
In a physical way, yes. So for today's Depth Dive, we are looking at a paper that basically argues the universe isn't just a big empty room, it's a mechanism. And for the most advanced civilizations, that mechanism acts like an inescapable trap.
And the paper we are looking at is by Nkumalan Nasanjargal. It was published just this year, 2026.
Hmm.
And I have to give the author credit because the title is just a masterpiece of academic density. Let me try to get this right.
Good luck.
It's called Cosmological Constraints on Technological Expansion within the infinite fractal descent framework. And it actually keeps going from there.
Yeah, it is definitely a mouthful.
I honestly felt my brain expanding just reading the abstract. But let's try to cut through that academic jargon for a second. What exactly is the infinite fractal descent? Because I got to be honest, it sounds like a sci-fi horror movie.
It really does. But it's actually this radical rethinking of cosmology. So Nizanjagal argues that we need to stop viewing the universe as just this random explosion that's slowly drifting apart. Instead, he models the whole universe as a discrete, stepped, recursive algorithm.
Okay, so wait. That sounds like he's saying we're living in a simulation?
No, not a simulation, a process. It's better to think of the universe less like a random sandbox and more like a massive industrial refinery. The paper refers to galaxies as spatial processing engines.
Processing engines.
Right. Their physical job, basically the reason they exist structurally, is to refine matter, to take all that chaotic raw hydrogen from the early universe and process it down step by step into complex, highly ordered systems.
So you're saying we aren't just inhabitants of the galaxy. We're essentially the product it's manufacturing.
In a sense, yes, we are the final result of a very long, very specific filtering algorithm. But here is the catch. The paper argues that for a galaxy to actually produce an informational anchor.
Which is Nozan-Jargal's term for an intelligent observer, right? Like you and me.
Exactly. For a galaxy to produce an informational anchor, it has to hit this nearly impossible sweet spot.
A Goldilocks galaxy.
Basically, yeah. The paper calls this state stable fractal synchronization, and it outlines two really massive requirements to achieve it. First, you need gravitational chirality.
Which is just a fancy word for spin, right?
Specifically, a very stable, consistent spin. You need a consistent rotational torque to organize all that raw matter into stable orbits that can last for billions of years without just falling apart or colliding.
Okay, that makes sense.
And in spiral galaxies, this is usually provided by a central barred structure. You know how the Milky Way has that distinct rectangular bar of stars right across the core?
Yeah, the engine room, basically.
Right, that bar acts as a massive stabilizer. But the second requirement is even harder to hit. You also need low fundamental tension.
Tension meaning what, exactly?
Meaning you need a neighborhood that is incredibly quiet. No frequent supernovae popping off, no massive radiation jets from active galactic nuclei at the core. High tension basically resets the algorithm, it sterilizes everything and prevents complex life from forming.
So you need a galaxy that spins perfectly to organize the matter, but is also quiet enough not to fry it.
Precisely. And when you actually look at the data, specifically they used the Sloan Digital Sky Survey for this, and you filter for spiral galaxies that are true Milky Way twins, meaning they have that barred center and that super low tension environment.
Let me guess, it's incredibly rare.
It's about 1.2%. That's it. And even within those rare galaxies, you still have to be living in the quiet suburbs, like our Orion Cygnus spur. So just by being here, listening to this, you are already occupying a statistically rare piece of real estate.
Okay, so step one of the cosmic filter is just getting a planet that doesn't get completely sterilized. But this is the part of the paper that took a turn I really didn't expect. Because we normally assume that if a civilization actually survives this filter, they inevitably become Star Trek. Right.
the natural progression.
They build ships, they explore, they colonize the galaxy.
And that assumption is exactly what this paper dismantles. This brings us to the core thesis of the whole framework, which is the metallicity paradox.
This was the real aha moment for me. Because usually when astronomers look for exoplanets that could harbor life, they specifically look around high metallicity stars. Because you need heavy elements to build planets in the first place.
Correct. And just to clarify for the listener, in astrophysics, metals are just anything heavier than helium. So carbon, silicon, iron, titanium. You need these elements to build a solid rocky planet, and you absolutely need them to build a technological civilization.
Right. You can't exactly build a microchip or a combustion engine out of floating hydrogen gas.
Exactly. You need refined matter.
So logically, you'd think the more metal a star system has, the better the chances for a really high-tech civilization to evolve there.
And that is exactly the trap.
Walk me through this. How does having more resources actually make you stuck?
It all comes down to density. If a planetary system is rich enough in heavy elements to actually support a highly advanced Silicon Age civilization, those heavy elements don't just float around in a void, they accrete. They clump together and form the planets.
Right.
So the typical homeworld of a genuinely high-tech species isn't going to be a small, low-density rock like Mars. It's going to be a super-Earth.
A massive, deeply rocky world.
A world with a solid surface, but absolutely packed with heavy elements. The paper uses a real-world exoplanet as a case study for this. KOI 456.04 in the Kepler 160 system.
I actually looked this one up while prepping. It's an absolute beast of a planet.
It's the perfect example. It has a physical radius less than twice that of Earth, so it's not huge in size. But because it's so incredibly dense, its mass is roughly 10 times that of Earth.
10 times the mass. So what does that actually do to the gravity down on the surface?
It cranks the surface gravity up to about 2.7 Gs.
Okay, let's just pause on that for a second. 2.7 Gs. If I weigh, say, 180 pounds here on Earth, on that planet, I'd weigh, what, almost 500 pounds?
Yeah, just standing up to get out of bed would be like carrying 2 full-grown adults on your back, 24/7.
That sounds miserable.
It does, but biology is adaptable. Maybe they evolve as short, stocky, multi-legged creatures with incredibly dense bones. Biology finds a way. But rockets cannot adapt. Physics doesn't care how strong your bones are.
Right. This is the rocket equation part of the paper. And I've heard of the rocket equation before. It's basically the rule that says you need fuel to lift your fuel.
Yes, Tsiolkovsky's limit. It is often called the tyranny of the rocket equation because it's exponential, not linear. On Earth, our escape velocity is about 11.2 kilometers per second. And doing that is already incredibly difficult. It takes a massive amount of concentrated chemical energy to break Earth's grip.
We barely pull it off.
Exactly. But on a super-Earth like AOI 456.04, the escape velocity isn't 11. It is over 26 kilometers per second.
I mean, that doesn't sound that much worse just saying it out loud. It's just a bit more than double.
Right. In purely linear terms, it's just double. But in exponential fuel terms, it is an absolute catastrophe. Plus, you have to factor in the atmosphere. A highly massive planet holds onto a much thicker, denser atmosphere, so the aerodynamic drag is immense. The paper estimates that the actual delta V, which is the total effort needed to reach orbit, is well over 30 kilometers per second.
Okay, so the math is punishing. But the paper gave these physical examples that just completely broke my brain. The sheer scale of what you'd need to build just to leave the ground.
Yes, this is where the gravity trap becomes an actual physical prison. The author ran the numbers for a standard chemical rocket, using hydrolox fuel, which is liquid hydrogen and liquid oxygen. Basically the most efficient chemical thrust we have. Let's take the James Webb Space Telescope as a payload.
Which is big, but it's not insane. It's about 6.2 tons. We launched it on a standard Ariane 5 rocket.
Right. A very standard, normal-looking rocket. Now, if you are an advanced civilization on that super-Earth and you want to launch that exact same 6-ton telescope into your orbit, you can't use an Ariane 5. The paper calculates that the fuel mass required for that single launch would be 55,000 tons.
55,000 tons of just fuel.
Just the fuel. To give you a visual on that, that is roughly the mass of a modern Iowa-class battleship.
Wait, so you have to engineer a flying fuel tank the size of a World War II battleship just to launch one single telescope into space?
Yes, and that's just for a small unmanned mission.
Oh, God. What about putting a person up there?
Let's look at an Apollo-sized mission. 3 crew members, a command capsule, a small lander. On Earth, we accomplished that with the Saturn V rocket, which was huge. On KOI 456.04, the fuel requirement jumps to 440,000 tons.
440,000 tons. I can't even picture that. What is that comparable to?
That is roughly the mass of the Great Pyramid of Giza.
So to get 3 alien astronauts into orbit, they have to launch the Great Pyramid.
Essentially, yes. And this is exactly where the engineering stops being merely difficult and becomes physically impossible. You cannot build a rocket the size of the Great Pyramid
Just because of the gravity.
because of the structural load limits of physical materials. Imagine a metal structure that heavy, completely hollowed out, and filled with highly volatile liquid fuel sitting on a launch pad in 2.7 g gravity. The bottom tanks would have to support the sheer weight of a stone mountain multiplied by nearly 3.
Would just crush itself.
It would pancake under its own weight long before you even lit the engines. The material strength required to hold that much liquid mass in a vertical column against that kind of gravity simply does not exist in nature.
So it's not just an economic issue where it's too expensive. It's that the laws of physics simply say no.
Physics slams the door shut. The paper argues that for these high metallicity, resource-rich civilizations, chemical escape is strictly forbidden. They are stuck at the bottom of a gravity well that is literally too deep to climb out of.
That completely flips the script on all those alien invasion tropes.
Yeah.
We always picture them building massive armadas and coming here. But according to this framework, the smarter they are and the better their home planet is for developing technology, the more permanently stuck they are.
Nissan Jargal calls them stagnant observers because they can definitely build incredible ground-based telescopes. They can look up and see the entire universe in high definition, but they can never touch it. They are forever isolated on these islands.
Okay, but this brings up my next big question. If they are stuck on these planetary islands, why aren't they shouting at us?
Right.
I mean, even if they can't physically leave, an advanced civilization could easily build a massive radio transmitter and just blast hello into the void. So why the silence?
This is the second layer of the trap, and it has to do with thermodynamics. The paper refers to this phase as the coherence transition.
This part of the paper got a little heavily technical with words like entropy and decoherence, but the core idea is really just about heat, right?
It's about the inescapable cost of doing business. Think about our own technology right now. Data centers, supercomputers, crypto mining, they get incredibly hot. We spend a massive fortune just trying to cool them down. Now scale that up. Imagine a planetary-scale civilization running quantum simulations, global AI networks, advanced manufacturing.
That is going to generate an unbelievable amount of waste heat.
Exactly. Current technology, what the paper calls decoherent technology, which is loud, radiative, and burns energy, inefficiently creates what Nassim Jargal calls decoherence pressure. It's noisy and it gets hot. The paper argues that there is a hard thermodynamic limit to this. If an advanced civilization keeps building that kind of loud tech, they will eventually just cook their own biosphere. They hit a state of metabolic overload.
So to avoid literally boiling their planet, they have to completely change how they compute and use energy.
They are forced to switch from decoherent systems, which are hot and loud, to coherent systems, which are phase-locked, silent, and perfectly efficient.
Break that down for me. What does a coherent civilization actually look like to us, looking through a telescope?
It looks like absolutely nothing. It looks exactly like the background void. A coherent system perfectly recycles its energy. It uses internal photonics, maybe closed-loop quantum networking that doesn't leak any stray radiation. To the outside observer, they transition from being this noisy, blazing radio source to being functionally invisible.
So they basically go into full stealth mode.
But not for military reasons, simply for thermodynamic survival. They stop screaming their presence into the void because they literally cannot afford the energy waste. So ironically, right at the exact moment a civilization becomes advanced enough to meaningfully communicate across the stars, the laws of physics force them to shut up.
That is deeply tragic. They are physically trapped by their own gravity and silenced by their own efficiency.
And there is one final brutal lock on the prison door. Because even if they somehow manage to invent a non-chemical way to escape the gravity, and even if they decide to waste precious energy to signal us anyway, there is still the issue of the spatial processing engine we talked about earlier.
You mean the vast distances between them?
The paper calls it the logistics of reach. Because habitable zones are spread out so thinly by the galactic algorithm, the physical distance between these successful anchors is unimaginably vast. Let's go back to our hypothetical friends on KOI 456.04. Let's say they invent some miraculous nuclear fusion drive, they beat the gravity trap, and they launch a ship heading straight for Earth.
They're finally coming to visit the neighbors,
That trick is over 3,100 light years away, even if they have a magical drive that can accelerate at one constant g for the entire trip.
which triggers relativity. Time dilation kicks in.
Exactly. For the actual crew on that ship, the trip might only feel like, say, 15 or 16 years. It's a long voyage, but completely doable. They write their memoirs, they play cards, they do research. But when they finally arrive and look out the window,
What do they actually see?
they see that time hasn't stopped for the rest of the universe. By the time they arrive at Earth, over 3,100 years have passed in our timeline.
So the Earth they set out to visit is completely gone, or at least radically changed.
And the home planet they left behind is ancient history. If they turn the ship around and go straight back, they will have missed over 6,000 years of their own history. Their civilization has likely risen, fallen, evolved into something unrecognizable, or just forgotten about them entirely.
You essentially become a ghost. You aren't an explorer anymore. You're a time traveler with a one-way ticket into the future.
The paper calls this temporal isolation. The physical geometry of the universe separates these islands of intelligence so effectively that physical contact becomes completely meaningless. You are always permanently out of sync with everyone else.
You know, when we started this deep dive, I thought this was just going to be another space is just too big theory. But this hits different. It feels almost deliberate. The gravity holds you down, the heat forces you to be perfectly quiet, and the sheer time separates you from ever reaching out.
It really does feel like a cosmic quarantine, doesn't it?
It genuinely does.
Yes.
So where does that actually leave us? Because the paper ends on a note about Earth specifically that I found surprisingly hopeful. Or, well, maybe just deeply ironic.
It is the ultimate cosmic irony. Under the infinite fractal descent framework, the paper classifies Earth as a shallow well anomaly.
Which kind of sounds like an insult, honestly. Shallow well.
It basically means we are the runts of the galactic litter. We are living on a planet that is surprisingly small, with a planetary core that is just dense enough to give us a protective magnetic field, but light enough that the gravity doesn't crush our ambitions.
We're hitting that Goldilocks zone again, but this time for gravity.
We are existing purely in the margin of error. If Earth were even 50% larger in mass, which is extremely common for rocky planets in the galaxy, we would be permanently stuck. We would never have had the Apollo program. We would never have launched satellites or the Webb telescope. We would just be looking up, dreaming about the stars, but never, ever leaving the atmosphere.
So we aren't the rulers of the universe. We aren't the most advanced or the oldest or the most resource-rich civilization out there. We're just the escape artists.
Exactly. We very well might be the absolute only species in our entire galactic neighborhood capable of physically leaving our cradle. Not because we are the smartest, but simply because the walls of our cradle happen to be just low enough to climb over.
Wow. That completely changes how I look at something as routine as a rocket launch. It's not just a feat of engineering, it's a cosmic loophole. We are literally exploiting a glitch in the spatial processing engine.
We are actively defying the algorithm, and I think that makes our space program and our very existence infinitely more precious. We are successfully doing the one thing the universe seems explicitly designed to prevent.
That is a heavy, heavy thought. But I want to leave you, the listener, with one final idea to chew on that builds on all of this. We spend so much time looking through our telescopes for these massive, perfect super-Earths, thinking they are the ultimate paradises for life. But what if the very thing that makes a planet perfect for life and abundant in resources is exactly what ensures its inhabitants can never, ever leave? What if the universe is just full of these luxurious, solitary confinement cells, and we, on our tiny resource, poor little rock, are the only ones actually walking around out in the yard? Maybe our destiny isn't to join some grand galactic federation. Maybe our destiny is to be the messengers for a universe full of silent prisoners.
That is a fascinating way to look at it. So, enjoy the low gravity while you can. It's a very rare privilege.
I certainly will from now on. Huge thanks to Ankam Gallant Nassan Jungle for publishing this paper. It's an absolute brain melter, but in the best way possible. And thank you to you, the listener, for sliding down the fractal descent with us today. Keep looking up and be incredibly glad you can actually leave the ground. We'll catch you in the next deep dive.